So today we're going to make another attempt at the Wall&Sign assessment type problem. This is a pretty classic physics problem where you have a boom arm that's free to rotate around a pulley or a pivot here attached with a string, and the boom arm has length of mass, or length L, and mass, we're going to say little m. Hanging from here is a 10 kilogram sign, and we'll say it's hanging a quarter of the way over at a distance of L over 4, and it has mass 10, and we're going to call that big M. So the question is, what is the tension in the string that holds it steady? So to do this, because it's a rigid object free to rotate, what we have to do is we have to draw a force diagram for the whole boom arm. So first let's draw the force diagram for the whole boom arm. A couple things we know about the boom arm is that it has its own mass, which means it has its own weight. So that weight, because it's it's a uniform object, acts at the center of mass. And so the Earth pulls it down here, and we're going to call that little mg, and that refers to the weight of the object acting at the center of mass of the boom arm. In addition, we have this one over here, a quarter of the way down. It's pulling down with some more massive, so it has a bigger force. We're going to call it big mg. That is the weight of the object. Now, in a technical sense, it's hanging by a string, so the weight is pulling the string down, and the string is pulling the boom arm down, but we'll assume that those are the same kind of things. Over here you have the actual string pulling it, and I think it's given to you an angle 36.9 degrees, but the angle itself doesn't matter. But we know it's pulling in this direction. So it's pulling in that direction. So this is the tension in the string here. We'll call it T for tension. And it's pulling up and to the left, so in a sense we're going to figure out how much is up and how much is left. Eventually we're going to call this one T in the y direction, and this is the T in the x direction. So these are the three obvious forces, but then you consider the fact that it's attached to the wall at this pivot point, so the pivot point has to also push. So in a conceptual sense, we know that if this is the T in the y direction that's up, it's the only up force, so the wall has to be pushing up also to balance these two downs. Also, if the string pulls it some to the left, the wall has to be pushing some to the right. So we don't know how much the up force is, but we know how much the right force has to be because it has to balance this out. So the way I think about it is that it has to be enough up force to balance these downs with this up, and enough over force. So I think it probably looks something like this. Now, we're going to go back eventually and look to see if this is true, if we're going to solve for this force. But I'm going to call this W for the wall force. So there's your force diagram. I'm going to call this one W in the x direction, and this one will be W in the y direction. So how do you go about finding the tension in the string? Well, the tension in the string can be found by analyzing the torques on my actual boom arm itself. The first step to analyzing the torques is to decide on a pivot point. So since this is the actual pivot point here in the physical setup, I'm going to use that as the pivot point here. What that means is that this mg will supply a torque, this mg will supply a torque, this tension will supply a torque in the opposite direction of those two, but this wall force doesn't supply any torque at all because of the fact that it is at the pivot point. So because the radius is 0. So we conceptualize torque as a general idea. A torque on an object is equal to the distance from the pivot point times the force that's acting times the sine of the angle between these two vector quantities. So what do the torques on this look like? Well, I'm going to write in what we call a net torque statement, and we're going to see what these do. So the wall doesn't supply any torque, but this mg supplies a torque, so what's its distance? Well, its distance is L over 4. That's the R value. The F value is big mg. And if I were to look at these values, if this was be my R vector, these would be 90 degrees between them. So when I go to put in sine of 90 is 1. This little mg also applies a torque. It's at L over 2. Little mg is the force. And again, the sine of the angle between them is 90 degrees. So sine of 90 is 1. And the last one, the tension supplies a torque. It's at a distance of L. And the angle between these two is our 36.9 degrees. So I'm going to say sine of 36.9 degrees. So we didn't put signs in here yet because we have to decide what's positive and what's negative in terms of the torques. We use the unit circle connotation where this direction, the clockwise direction, is negative and the anti-clockwise direction is positive. So this force acting by itself would cause a torque in the negative direction. So with the little mg, and this would be plus. Now, when I look at my whole object here, it's not accelerating at all. So therefore, what do I know about the net torque? It has to be 0. So if this is net torque and this is net torque, so this is equal to 0, so what I end up with is a statement that looks like this. LT sine 36.9 is equal to L over 4 big mg plus L over 2 little mg. Since I have an L in each term, they magically disappear. And I end up with T sine 36.9 is equal to mg over 4 plus little mg over 2. If I go and plug and chug these, I end up with big mg, which is 10 times 10 over 4 plus little mg, 4 times 10 over 2. And that's all divided by the sine of 36.9. And it turns out T is equal to 75 newtons. So once you have the fact that T is equal to 75 newtons, you can start to analyze the rest of the problem, because the next question asks me, can we calculate the force exerted by the wall? So if I want to calculate the force exerted by the wall, I think I'm going to need to use a net force statements. We're going to need to use some net force statements in the horizontal and vertical direction. So let's start with the horizontal direction because it's a little easier. If I write a statement for the net force in the x direction, well, what I know is there's no acceleration in the x direction, so that must be equal to 0. The net force in the x direction, well, what do I have? I have w in the x direction minus t in the x direction. So if net force is equal to 0 and net force is equal to this pair, I know that the w in the x direction has to be equal to the t in the x direction. And conceptually that makes sense because if this is the only force to the left, it has to balance out the only force to the right. How are we going to find t in the x direction? Well, if I analyze my triangle over here, what I notice about this is that there's a relationship between the tension in the x direction, and the tension in the y direction. This is the angle that's given, but it's also equal to this angle right here. And so relative to this angle, the tx is the adjacent side. This is the hypotenuse, so this is actually equal to t cosine 36.9. If I go to plug and chug that, w in the x direction is equal to the tx, so this is t cosine 36.9. Our t value from earlier is 75, so I have 75 times the cosine of 36.9 degrees, and I end up with w in the x direction is equal to 60 newtons. Sorry for the pause. Okay. So that's the w in the x direction. What about the w in the y direction? If I don't do the w in the y direction, we're going to have to do a net force statement for the vertical. So the net force in the y direction, again, it's equal to 0 because there's no vertical acceleration. But what are my forces in the y direction this time? Well, the net force in the y direction, what do I have? I have w in the y direction, up, plus t in the y direction, up, minus big mg, minus little mg. Since net force in the y direction is this, and it's equal to 0, if I want to solve for wy, w in the y direction is equal to big mg plus little mg minus my t in the y direction. I can solve for these because I know that my w in the y direction is equal to my big mg, which is 10 times 10, plus my little mg, the mass is 4, the gravitational field strength is 10, and then my t in the y direction, if I go back here, the y is the opposite side here, so this is 75 times the sine of 36.9. So there's 100, this is 40, this is minus. Okay. When I do 75 sine 36.9, that value is 45. So I end up with 140 minus 45. So the w in the y direction is equal to 95 newtons. So that gives me my horizontal component. This gives me my vertical component. And let's see if they make some sense here. Could my wy be 95? Well, if we know that this is 100 down and this is 40 down and this is 45 up, this could be 95 up. That seems to make some sense. And in my picture it makes sense. And then this is 60, so if this is 45 and this is 60, it makes sense in terms of what the angle is. So conceptually it makes some sense. Let's answer the question. It says, what is the total force by the wall? And what is the angle? So what I notice is that my wall force squared should be equal to my wall force in the x direction squared plus my wall force in the y direction squared. When I go to calculate those, so my wall force in the x direction is 60 squared plus in the y direction it's 95 squared. So my wall force in the y direction, let's plug and chug it. I got to calculate this. Of 112 newtons. So that's fine with me. So that's 112. I'm okay with that. And then if I want to find the angle, what I realize is the tangent of this angle here. Now, because it's given me this angle in my original problem here, I'm going to solve for this angle here. So I'm going to call that theta. So the tangent of that angle, theta, in this case, the opposite side would be the wy. The adjacent side would be the wx. So then theta is equal to the inverse tangent of wy divided by wx. Inverse tangent. My wy value is 95. My wx value is 60. So theta is equal to
Oh yeah, multiply the whole thing.
57.7 degrees. So, the question says what is the force, the resultant force, and the angle, and there we go. The last part of the problem asks, if the string breaks, calculate the instantaneous acceleration of the far end of the boom. Well, what's interesting about that is I need to reset the whole problem because this whole problem here is predicated on the fact that there is a string. But if you cut the string, here, the tension is removed and the two mg's stay the same, but the wall force will change and this will completely go away. So let's take a moment and reset the problem. So the new force diagram will look like this.